upon and arranging. So it is what we're doing in an epitaxial process. We're going to deposit a material in its crystalline form, and we can do that only if we have a crystalline template underneath. And the idea of the epitaxy process is that the ordering of the crystalline material on which you do the deposition is continued in the growing layer. So you basically do a template matching. You have a crystalline structure, you put something on top by a physical or a chemical process, and you have a continuity of the crystalline lattice with some concerns in some cases. In order to have a good epitaxy process, you need to be able to see the crystalline structure underneath. And if you have an oxide on the surface, I told you earlier, if you have an oxide on the surface, you have an amorphous character. So there's no crystalline order. So you will not be able to have a crystallinity continuity on top of the oxide. You can still deposit a crystalline structure, but it will be polycrystalline. It will not be single crystalline. And there should be a lattice matching, because if the lattice here is completely different from the material that you grow on top, then obviously you will have defects and defectivity here at this interface. Here you see the simplest example. So if you do silicon epitaxy by using a chemical vapor deposition process, so silane, which will thermally decompose on the surface, leaving silicon and desorbing hydrogen, done at temperatures above 500 degrees C. You can see here what is happening here, and this red box is magnified here. Here, in this part, we had a hydrogen-terminated surface. So where silicon atoms are arriving on this crystalline matrix, and they follow the order. So you have a nice continuity of the crystalline order going up. Here, the light dashed area is oxygen that is present, so an amorphous nature. And the silicon atoms will still deposit, they will crystallize, but you see facets here indicating that you have different crystal grain orientations. Here it is the same single crystal process that is continued, so you will not be able to distinguish between the crystal here and the crystal here. Here you will have a polycrystalline nature, and that is typically what happens if you nucleate on an amorphous outer layer. It will be polycrystallinity. If you want to have that silicon epitaxy, then you need to have a nice oxide-free surface. This is in case of silicon on silicon. So if you put silicon on silicon, then obviously the crystalline lattice here and the crystalline lattice here is the same. So you will have a good continuity. They call this homo-epitaxy. In some cases, you will also have a different material deposited on a crystalline lattice. For example, germanium or silicon germanium. Now, the lattice parameters are different. So if you want to match a larger crystal on a smaller crystal, you will have strain. So you will have indeed a lattice matching, but whenever there is strain, whenever there is tension here, you can have dislocations and you can have defects. But that will be discussed more by colleague Delaby in her session. And then just one way, here you see one way of overcoming that strain is by introducing a buffer layer with a matching lattice parameter. So you have silicon, and we're just going to put strontium titanate on top of the silicon. So the difference between the silicon lattice parameter and the strontium titanate lattice parameter is small. So we'll have a little bit of strain, but manageable. And then we put barium titanate on top, which has a small gap between the lattice parameter of strontium titanate and barium titanate, which is again causing a little bit of strain here, but manageable. If we would do the barium titanate immediately on the silicon, then we would have a lot of defects, a lot of dislocations, a lot of problems there.